Hi, my name's Hugh Spence, and this is Brick, my glider for 1601's glider project. My task was to design, build, and test a glider that would fly over 20 feet with just an arm's throw. The requirements were that the glider had to be made primarily of the balsa wood provided, with some supplemental items allowed. It had to be no larger than 16 by 16 inches, and it must remain in one piece during the flight, and it must be hand-thrown with no remote or automatic control. The measure of success of my glider is the horizontal distance in my best throw during the tournament. Any vertical left or right distance is not considered. It will also be inspected beforehand in order to ensure it fulfills all of the construction requirements. Longitudinal stability is proportional to the positive distance between the center of gravity and the normal point. The normal point is the point where the lift vector acts through, which in this case is roughly 1/4 of the chord from the leading edge. A design choice I made because of this was shaping the body section to be inherently front heavy. Another way to increase stability is to add a horizontal and vertical tail section. I decided to add both, with the horizontal tail piece being 1/4 of the area of my wing. The size of my glider was ultimately decided by fate when I tragically destroyed my balsa wood sheet closing it in my drawer. The largest piece of wood left was the 27 by 7 centimeter piece of wood that ultimately became my wing. I decided to make my wingspan the span of this piece of wood and size my fuselage accordingly to be 75% of 27 centimeters. When choosing my wing shape, I had to think about two things: aspect ratio and wing area. My wingspan was pretty much set after my wood accident, so that simplified my choice. The designs I contemplated choosing from were a full rectangle, the size of my largest piece of wood, a skinnier rectangular wing, and an elliptical wing. Higher surface area means more lift, and a higher aspect ratio means less drag. An elliptical wing will have a higher aspect ratio than the same size rectangular wing, and therefore less drag. However, a rectangular wing will have a higher surface area and therefore more lift. What ultimately decided which option would have the highest chance of success was the fact that my glider will be small and therefore have a small profile and less profile drag. This meant I wanted to maximize lift as my glider could afford slightly more drag. For this reason, I chose to make the biggest rectangular wing I could, which was 27 by 7 centimeters. With my wing and tail made, I decided to test my glider by loosely attaching both with tape and throwing it in the hallway. You can't really tell in this video, but it backflipped almost instantly, meaning that I needed to shift the center of gravity forward so that it was in front of the normal point. Now to balance my glider, I needed to add something heavier than the balsa wood to shift the weight forward. The material ideally had to fit into a small space to avoid increasing outside surface area and therefore drag, so density is important. It had to be cheap because I pay enough for school already, and it had to be workable in order to fit in my cargo bay that I created. The materials that I decided to choose from were Play-Doh, lead fishing weights, and tungsten fishing weights, as they were all readily available to me. Tungsten is about 1.7 times as dense as lead, and about 13.5 times as dense as Play-Doh. So tungsten comes out on top for density. However, tungsten is the hardest metal found in nature, and so it is extremely unworkable. It was also 5 times the price of lead, so it definitely was not the way to go. Play-Doh and lead are both cheap, and although Play-Doh is easily moldable by hand, the amount needed would be far too bulky and increase drag too much. Lead is a very soft metal and can be shaped with a simple file, so I believe lead has the highest probability of success. In the end, I decided to use 1/2 ounce lead fishing weights and file them down so they fit in my cargo bay underneath the nose of my glider. I tested my plane using 1 and 2 weights. When the plane had 2 weights in, it went just a couple of feet further than 1 weight, so I decided to go with 2 weights in my final design. With 2 of the weights inside, my center of gravity was shifted to about 1/6 of the chord from the leading edge. My choices of adhesives for the plane were nails, superglue, and wood glue. When deciding, I had to consider the weight and strength of the adhesive. I did not want to pick an adhesive that would shift the center of gravity too much, and I also had to choose an adhesive that wouldn't break on landing. My mind initially thought to use nails for the wing. However, the balsa wood would just be too soft and I didn't want to risk cracking any of my last remaining pieces of wood. They would also shift the center of gravity undesirably. Superglue and wood glue are both negligible in how they affect the weight, and they both have similar binding strengths. However, I believed wood glue would have the highest probability of success as it dried slower and I had more time to ensure that my part were glued on perfectly straight. This was my final design. Rectangular wings, a tadpole-shaped fuselage with a weighted lead payload at the front, and a horizontal and vertical tail section for stability. For symmetric airfoils, the relationship between the coefficient of lift and the angle of attack is approximately 2 pi if the angle of attack is in radians. And this is especially true for thin airfoils. Now, my best flight happened when I threw it at an angle of 20 degrees. And so that's pi over 9 radians. Now, the equation that results from this is coefficient of lift is equal to 2 pi times the angle of attack. And so therefore the coefficient of lift is equal to 2 pi times pi over 9, which is 2 pi squared over 9, which is approximately 2.19 to 3 significant figures. For drag, the coefficient of induced drag is equal to the coefficient of lift squared over pi times the aspect ratio times the efficiency factor. For my glider, the efficiency factor is approximately 1, the aspect ratio is 3.86, and so therefore the coefficient of induced drag is approximately 0.396 by this math here. This video is my best throw in the competition, and the next is my best test flight, which was an absolute beauty. If in the future I was met with the same design constraints, I would personally try use less weight but shift it further forward, as the impact of the glider hitting the ground damages it when the ground is too hard.
Jeez.